Here we'll look at the symmetry of graphs. And there are a total of 3 different kinds of symmetry that we are going to look at. The first is symmetric with respect to the x-axis. X-axis symmetry means that for every point xy that is on the graph, x negative y is also on the graph. We essentially treat our x-axis like a mirror, and everything above should match everything below. As an example, if 4, 1 is on the graph, that means 4, negative 1 is also on this graph. Y-axis symmetry means that for every point xy that is on the graph, negative xy is also on the graph. If we think of this in geometric terms, now my y-axis acts like a mirror. Everything on the left has to match things on the right. Once again, in this case, if 4, 1 is on the graph, this means negative 4, 1 is also on the graph. The last symmetry we'll look at is symmetry with respect to the origin. This means that for every point xy on the graph, negative x, negative y is also on the graph. If we have a picture, this is essentially saying if I take this graph and rotate it 180 degrees, if I take my piece of paper and essentially turn it over, then it's still the same graph. We didn't actually change anything. Another example, if 4, 1 is on this graph, that means so is negative 4, negative 1. We can test equations for symmetry, and essentially we're going to go about this in 3 steps. The first thing I'm going to do is replace y by negative y. And if I do this and nothing in my equation changes, then I have symmetry with respect to the x-axis. The next thing I'll do is replace x by negative x. And once again, if nothing in my equation changes, this time I have y-axis symmetry. Finally, I'll replace both x by negative x and y by negative y. And if my equation doesn't change, then this has origin symmetry. And we'll do a few examples to demonstrate this process. Here's our first equation. Step 1 says to replace y by negative y. Now I have negative y equal to 3x squared over x squared minus 2. If I try to multiply both sides by negative 1, I get negative 3x squared over x squared minus 2. This is not the same equation, so we do not have x-axis symmetry. The second step, let's replace x by negative x. This time y is equal to 3 times negative x squared over negative x squared minus 2. And a negative number times a negative number is still positive. So here, nothing changed. I do have y-axis symmetry. Finally, we want to check if we have origin symmetry. So I'll replace both x and y. When I do this in this equation, the right becomes 3x squared over x squared minus 2, and I can see that I'm back in the first case, which didn't work out. So there's no origin symmetry. In this case, we have only y-axis symmetry. Next, we'll look at this equation. Step 1 says replace y with negative y. Since a negative times a negative is positive, this is the same thing as x squared plus y squared equal to 1, which is what I started with, so I do have x-axis symmetry. Next, I'll replace x by negative x. And since negative x times negative x is positive, I have x squared plus y squared equal to 1, which is still where I started. So this one also has y-axis symmetry. The third step is to replace both x and y. When I do that, once again, I have x squared plus y squared equal to 1. So this has all three types of symmetry: x-axis, y-axis, and origin symmetry. Therefore, it is possible to have more than one type.